So we know the notion of a span. A span is a subspace generated by k specific vectors. Okay? Suppose somebody gives you a span, a subspace generated by u1 to uk, and you pick any vector v, and you want to know, is it in that subspace? Okay? How do you determine? And that's what we're going to do by means of examples. So here's our first example. Let u1 be the vector negative 3, 1, negative 1. So this is a vector in R3. And u2 is going to be the vector 5, negative 2, 1. Two vectors. Okay. Is v, which is going to be the vector 1, negative 1, negative 1, in w, which is the span of u1 and u2? That's the question. Is v, that specific vector, in the span of these two guys? So let's start translating our question, and by translating it enough times, we're just going to see its solution. Okay? So the question is, another way of rephrasing the question is, can v be written, what does it mean to be in the span of these guys? Right. That being in the span means that it's a linear combination of u1 and u2. So our question is it in the span? It's the same question as, can v be written as v equals alpha 1 u1 plus alpha 2 u2 for some alpha 1 and alpha 2? That's the question. Do you agree? Okay. Except there's one problem, that I want to be consistent with my notes, otherwise I might get confused, and I didn't use alpha 1 and alpha 2 for reasons that you're going to see in a minute. I called it x and y. Can you live with that? Okay. So can v be written as a linear combination of these two generators? Can v be written as some x times u1 plus y times u2? Right? Okay. So the question is, so I'm translating it again. So can, oh, maybe let's not write can. So are there x and y, these are just numbers, we're working in R right now. Are there scalars, x and y, such that, ST is an abbreviation for such that, let's write it. X times u1, negative 3, 1, negative 1, plus y times u2, 5, negative 2, 1, equals v. 1, negative 1, negative 1. Do you agree that this is still the exact same question? Good? So are there x and y such that x times u1 plus y times u2 is precisely v? Now, this should look familiar. This is how we wrote a system of equations in our new way of expressing it as x as a linear combination of the columns of the coefficient matrix, right? So this would correspond. So again, the same question asked differently, is there a solution to the system coefficient matrix negative 3, 1, negative 1, 5, negative 2, 1 times x, y equals 1, negative 1, negative 1. Now it's written in ax equals b form. Do you agree that this is again the same question? Good? And we know how to solve a system of equations. right? How do we solve a system of equations? We write what we call the augmented matrix, right? We take this vector B, write it here with a vertical line, and start doing elementary row operations. Remember? So that's what I want to do. And I want to find out, is there a solution? If I can find a solution, that solution is precisely going to be an xy solving this, or an xy solving this, or an xy allowing this, namely giving a positive answer to this question. Is everybody with me? So let's solve this system. It's not a difficult one because it's a small system. Let's solve it. Good? Okay, so let's write the augmented matrix here. Negative 3, 5, 1, 1, negative 2, negative 1, and negative 1, 1, negative 1. Do you agree that this is the system? Okay. And now I want to get it to its reduced form, right? And I need to start doing row operations. Okay. And I hope that by now these are things that you feel comfortable with. Okay, that you've practiced a bit. So the first thing I'm going to do is switch rows 1 and 2. So I'm going to get 1, negative 2, 1, negative 3, 5, 1, and negative 1, 1, negative 1. Now I'm going to take...
It should be minus 1, top right.
Top right, negative 1. You're right. Thanks. R2, I'm going to replace by R2 plus 3R1. And R3, I'm going to replace by R3 plus R1. And I'm going to get 1, negative 2, negative 1, 0, negative 1, negative 2, 0, negative 1, negative 2. So I can see that you're checking my calculations, which is good. I'm just really copying it off my notes in order not to spend too much time on it. R3 I'm going to replace by R3 plus R2, and R2 I'm just going to replace by minus R2. So I'm going to get 1, negative 2, negative 1, 0, 1, 2, and 0, 0, 0. Good. And finally, all I need to get rid of is this negative 2 here. So I'm going to write R1, replace it by R1 plus 2R2. And I'm going to get 1, 0, 3, 0, 1, 2, and 0, 0, 0. Right? Now it's in canonical form, right? And it has a solution. The rank of A equals the rank of A star. Remember all those things? And in this case, we can even read the solution off precisely, right? We don't have to do any more calculations. X is 3 and Y is 2. It has a unique solution in this case. So, single solution. X equals 3, Y equals 2. Good? And now we can go back and plug that in and see that in fact we got V written as a linear combination of U1 and U2. So V was 1, negative 1, negative 1. And it can be written as 3 times U1, which was negative 3, 1, negative 1, plus 2 times U2, 5, negative 2, 1. And you can verify that this is indeed true. Okay, so the answer to our question was yes. V is a linear combination of U1 and U2. Okay, so note what happened here. We were asking a question about linear combinations, about spans. Our way of solving it was translating it to a question about a system of equations and solving the system. Good. What we did in the previous lesson was asking a question about a linear system of equations. Does ax equal b have a solution? And saying that it has a solution if and only if, and then phrasing it in terms of linear combinations and spans. If and only if b belongs to call A, or b is spanned by the columns of A, or b is a linear combination of the columns of A. Okay, so there's a translation going on back and forth between the notions of span and linear combinations and solving systems of linear equations. Do you see that? Okay, and it's in fact in both directions. So let's remark that. Remark. Let's say, this is not a precise remark, but let's say questions about spans and linear combinations can be translated to systems of equations. And vice versa. Okay. Now there's a word of caution here. In this course, in fact, throughout this course, many things we're going to see can be translated to systems of equations. And one of the most common errors in this course is you get a question in your exam, and you see the data, you write a linear system and solve it. Sometimes it's related to the questions and sometimes not. Okay, so it's not that we just take whatever question we get and translate it to a system, or translate it to row operations on a matrix, or often that's involved in the solution, but it still requires thinking, right? We went through a few steps of thinking before doing the actual translation to what do we need to take? Do we need the columns? Do we need the rows? Do we need row operations? Do we need to do something else? Okay, so it's not as easy as whatever question you get, just write a matrix, start doing row operations, get to the canonical form, and poof, you're done. Okay, you can always take a matrix and do that, but how does what you get relate to the original question is sometimes not clear, or sometimes not related. Okay, so you have to be careful about getting too fond of just taking things and translating them to systems of equations. You have to do it in a meaningful way. That's what I'm trying to say. Okay, so there's still thinking involved, a lot of it. Okay, and that's one of really the common errors, that it's just, people just take something, boof, write a matrix and start doing row operations, and it can be totally unrelated to the problem they're dealing with. Okay? Okay, let's do another example, one more example. Here I'm not going to do the details. I'm going to leave it to you just for practice. Okay, because just to show you what sort of questions can, for example, be asked. So suppose we have a vector with 5 entries, a 5 tuple here. And does it belong to the span of these 4 vectors? 1, 2, 1, 3, 7. 1, 1, -3, -5, -6. 1, -1, -2, 2, 0. And 1, -3, -1, 2, -1. Question mark. Is this vector spanned by these 4 generators? Translation. Can we write this as a linear combination of these 4 guys? Translation. Is this equal to x times this plus y times this plus z times this plus w times this? Good? Translation is there a solution? Is there a solution to the system? And now I'm going to take this to be B and these to be the columns of A. And I'm going to name the variables X, Y, Z, and W. And the system is going to be the following. X plus Y plus Z plus W equals 2. 2x plus y minus z minus 3w equals, I called it, never mind, equals 14. In my notes, I called them wxyz, which actually makes a lot more sense, right? Let's do that. Let's not be lazy. The reason I'm being very strict on following my notes is that often I take examples and recall them in later discussions, and I want them to be consistent with, so if I say in 5 lessons from now, hey, look back when we discussed determining whether vectors belong to a span or not, the example with a 5x5 or 5x4 matrix, I want you to see the exact same one that I may write again and said, hey, we solved it and this is what we got. So sorry for rewriting this. W plus X plus Y plus Z. And then we have 2W plus X minus Y minus 3Z. And then we have what? W minus 3X minus 2Y minus Z equals negative 3. And then 3W minus 5X plus 2Y plus 2Z equals negative 15. Good? Is everybody following how I'm getting these equations? And finally, 7w minus 6x, no y's, minus z equals negative 2. And this you need to solve. Okay, write the augmented matrix, the coefficient matrix, the column. Start doing row operations. There are going to be quite a few of them just because it's a big matrix, right? And answer. I'm not going to do the row reduction business. Yes. And I'm even going to tell you what it is. There's a unique solution here. W equals 2, X equals 3, Y equals negative 1, and Z equals negative 2. There's no degrees of freedom, and these 5 equations determine a unique solution in this case. Okay, it's not something you can see from 5 equations automatically. You have to do some stuff. Okay, good? Okay, so I guess this is the end of this one, and yeah, there's another notion which we're going to discuss in the next lesson.